Last time we left off talking in section 6.1 about rational numbers, which is what this whole chapter is going to be about. And we left off on Theorem 6.3, and 6.3 and 6.4 are on this slide. So 6.3 talks about how to determine fractions being smaller or greater than another fraction. So it tells us that if you have integers a, b, and c, and you need the value for b to be greater than 0 to make this work, then if a over b is greater than c over d, that's only going to happen when a is greater than c. That's why the b value needs to be positive for that to happen. And the reverse is true if b is negative. So all they're saying is that if the denominators match and they're positive, you can rather ignore the denominators and just compare the numerators. Okay, that's all this one is telling you. Now, if they're not the same denominators, this next one is similar to one we encountered last time, and it's telling you how to sort of make up for that fact. So if you have, again, a, b, c, and d in their integers, your b value and your d value are greater than 0, and you have one fraction larger than the other one, that will happen if and only if you can do this cross multiplication. And so you're looking at this diagonal, multiplying them, and then the same thing for the other one. So the first diagonal, AD, is greater than BC. So the direction of the inequality is the same if you start with the top left-hand corner and write that one down first, basically. And there's nothing special about putting the greater than sign there. If the less than sign were in any of these, the same thing would follow. You would just have to have the less than sign in both inequalities. Okay? So what we're going to do next is we're going to take a look at three fractions, and we're going to write them in ascending order. There's lots of ways to do that. One way is we could use the theorems that we just discussed. Sort of the inherent problem with the theorems that were above is that they compare two fractions, and this is comparing three. So that's not especially friendly for comparing three fractions. It would be friendlier if we compare three fractions to actually get all the denominators the same, and then using Theorem 6.3 would be a little bit easier because all the denominators match and we can just look at the numerators. So we're going to try using Theorem 6.3 to help us with this one and get all those denominators the same. These denominators happen to be very nicely similar already. I have a 20, a 10, and a 5. So what would I get if I wanted the least denominator that they would all have in common? Well, 5, they're going to have a 5 in them, but 5 won't work because I can't turn the 20 into a 5. But we can do 20, and then we can turn the 5 and the 10 into a 20 instead. So they'll have a 5 in them. They'll all have a 5 in them because they have that 5 in common. We can change all of them to have a denominator of 20, though. Okay, so right now I'm not putting them in any kind of order. I'm just going to change them. The first one's already got a denominator of 20, so that one's good. But the 3 over 5 doesn't. So how am I going to get this one to have a denominator of 20? Right, multiply it by 4 over 4, actually, right? So if I multiply it by 4 over 4, what am I going to get on the numerator? 12. Good. Now the second one, or the third one rather, is 7 over 10. How am I going to get it to have a denominator of 20? Exactly, 2 over 2. So if I multiply by 2 over 2, what do I get on top? 14. All right, so this one says ascending order, so that means smallest to greatest. You know, they go up in order, ascending like you ascend on a staircase. So what is the smallest one of these fractions that I've rewritten, the ones I've rewritten down here? Which one's smallest? The 12 over 20. So this one's the smallest. Let's just write number 1 here. Here's number 1. Which one's second? 13 over 20. This one's second. And then this last one, 14 over 20, would be third. Now, we need to make sure, though, that we answer the question the way it was asked. That is, that I was originally given fractions that had denominators 25 and 10. So I'm going to use those fractions when I write them in the correct answer, you know, the ascending order answer that I'm asked to find. So we're going to use the middle fraction's original form, which was 3 over 5. And I'm just going to use the less than sign. If you use a comma, that's fine as well, but I'm just going to reemphasize by using that sign which direction I'm going in. The second one was 13 over 20, and that's actually the way that it was given to us. And the last one's 14 over 20, but it was given to us as 7 over 10. Yeah. So this would be the answer that I would get by doing that. Does that make sense? Now, could I do the cross multiplication thing? Yeah, I could. It's just going to be more complicated on this one because I've got those 3 fractions to compare instead of just being able to get the denominators the same and then comparing it using Theorem 6.3. All right, now this one's comparing just 2 fractions. And there's lots of ways to make the decision, but we could use Theorem 6.4. And since I haven't used it yet, that's the one we're going to try this with. Okay? I'll show you a couple other options on this one, and we can talk about in other ways maybe you might want to think about solving this one. But one way to do it would be using Theorem 6.4. So using Theorem 6.4 means that I would multiply this diagonal together. So what is 21 times 215? 4,515. Okay, and what about the other diagonal? What is 51 times 430?
21,930.
All right, so which one's bigger?
21,930.
Yeah, the red one, the 21,000, is definitely larger. So the symbol that should go there is actually the less than symbol. The first one is less than the second one. What that means is that in the original fractions, as we were given them, I also have a less than sign between them. Now this isn't the only way to do this problem. It's fine. It's not especially pretty actually because the values are really large. You probably used your calculator to do it. It wasn't quick and you could multiply it in your head. So taking a look back at those original fractions, they actually have a nicer way of doing the particular problem because of the fractions that were given. Did anybody think to try something different than what we just did before I said, hey, let's try 6.4? Yeah, what did you do? Or what did you think to try?
Common denominator.
Yeah, I think common denominator is probably the simplest way to go here. What would the common denominator be?
430.
Yeah, the 430s just double the 215, right? So if I doubled this 215, whoops, and I doubled the numerator, then I would actually have the 51 times 2 is 102 over 215. Not 215, excuse me, 430. And I'd have the 21 over 430, right? And then very clearly I've got the same denominator. I'm back to using Theorem 6.3, and I would actually have this sign in here because of that. Yes, Karen?
There's also another way to do that. We could use it, we could relate it to other fractions that are closer to us, like
Yes.
50 out of 200,
Mm-hmm.
and 20 out of 400 or 440.
Yeah, and that's a really good way to think about it. So a lot of times fractions are not very pretty. I mean, these particular fractions are kind of ugly to look at. But if we estimate them using fractions that are a little bit more common to us, right, it would actually be really nice on this particular one to see that the first one's smaller. So if you take a look on the first one, that 20 over 430 is about 20 over 400. Agreed? So this is an awful lot like the number 1 over 20. Okay? You just cross out one of those zeros right at the end. And then this 2 and this 4 reduced to 20 on bottom. And you can do the same thing on the second one. The second one, okay, hang on. Let me move some of this over. The second one is 51 out of 215. Well, more or less we're looking at something that's about 50 over 200. And when you're looking at the 50 over 200, and if you simplify this one, those zeros cancel. And then you've got 5 over 20, and that's actually 1/4. Well, 1/4 is a lot bigger than 1/20. So, and you don't even have to write down that those equivalent, and they aren't even equivalent, but estimated fractions. But almost when you're looking at them, you should say, look at this. The numerator's smaller and the denominator's bigger. Definitely going to give me a smaller fraction. I can't have a smaller numerator and a bigger denominator and get anything possible to make that big. So there's a lot of ways to approach the problem. You don't have to do it in one particular way. Any of those would be fine. All right, let's take a look at Theorem 6.5. Theorem 6.5 is actually a really important theorem. It tells us that if you have 2 rational numbers, there's always another rational number between them. And this is unique because this does not happen with natural numbers or whole numbers or integers, which are the 3 sets of smaller types of numbers that we talk about in Math 1. You can't do that, right? So like if you have the integers 3 and 4, there's not another integer between them. There's other numbers between them, but not integers, because integers are whole values. But we can do this always with rational numbers. So whatever two rational numbers you want to give me, I can always find something between them. And there's several ways to do that. Theorem 6.6 actually gives us one way to do that, which is kind of clever. And it's especially nice if you don't happen to have an obvious value between them. For example, if I give you 5 over 10 and 8 over 10, you know 6 over 10 and 7 over 10 are between them, right? This theorem that's written right here is really not all that helpful for that situation. But if we're looking at the values 1/5 and 1/4, I mean, you're going to have to do a little bit of mathematics to actually find something between them, whether it's changing it into decimals, using your the fraction pieces of your calculator, using your calculator and the fraction buttons in your calculator to do that. But this is another nice way to actually do this that's really quick and easy. What this is telling you is that if you have two fractions, one smaller than the other one, if you add the numerators of the fractions together and you add the denominators of the fractions together, the resulting fraction will be between the two fractions you started with. That's really handy because it's a very simple thing to do because all it involves is addition. No calculator even needed. So if you're taking a look at this particular one, I have 33 over 427 and 34 over 427. 33 and 34, they don't have anything between them that's a whole number, right? If I change it and I say, oh, but 33 and a half is between them, that's fine, and you could do that, but then you're still going to have to do more math after that in order to get rid of the decimal involved in the middle of your fraction. So, although that's one way to do it, let's take a look at how we can do that with this particular theorem. All this theorem tells us that we're going to do is we're going to add the numerators together, and we're going to add the denominators together. So, what is 33 plus 34? 67. And 427 plus 427. And the denominators wouldn't have to be the same for this to work. They just happen to be on this particular problem. 854. Now, in general, we would want to look and see if there's any way that we can reduce this. Let's see if I wrote anything down here. I don't think that there is on this particular one. I think 67 is prime. But at this point, you might actually end up with something that they're both even, or they both have a 3 in them, and you can reduce them. So you would want to be able to do that at this point. But on this one, we're finished. Okay? And that's it. That value is between the two that you looked at. If you wanted to verify it to yourself just to make sure you didn't make an error, or you were doing it and you couldn't quite remember if that's how the theorem went, you could actually turn all three of them into decimals and take a look at their decimal expansion. You can't justify to me that that's going to work right now because we haven't really talked about decimals. That's in Chapter 7. But if you'd like to take a look at those decimals and make that sort of a judgment call, that's another way you could check your answer. All right, here's example 6. Why must there be, I got a typo on that one. Why must there be a number between these fractions? Okay, that's exactly along the lines of what I want you to be thinking about. So when you're thinking about space, I'm hoping the way you said it, you're thinking about a number line.
Yeah.
Yeah. Okay, so let's draw that. So on a number line, and if you've done this before with your calculators, because you've all had some kind of a course where you've seen graphs that zoom in on something, where if you zoom in on a graph really, really close, you can see much tinier fractional values or decimal values, right? So if we were to zoom in on this portion of the number line, somewhere we would be able to see that we have 33 over the 427, and we've got the 34 over the 427. So are they close together? Yeah, they're very close together. But if we zoom in, there's space between them, just like Ali said. So if there's space between them, that space between them has to have some kind of a numerical value. It's a number line. It's continuous. It doesn't have any gaps in it. There's no blank spaces. So go ahead and write down a couple of sentences of that justification that we just talked through on this one, talking about that space issue. Okay, so I'm going to give you guys just a minute or so to write that in, and then we'll move on to the next slide. Right. I was about to say periodically. It's probably a little bit more regularly than periodic. You're going to have questions in your book that are going to have students work, and the questions will ask you to respond in some way to that student. And so that's a really good practicing opportunity for you, because that's what you're going to do at some point, is you're going to have some student in your class that's going to ask you some random question, and you're going to have to respond to them, okay? So this is the kind of questions that I find to be very helpful in ascertaining whether or not you really understand how to explain this to the student. So this is some student work. The student has taken the fraction m plus n over p plus n, and they have reduced it to m over p. And they'll ask questions that are sort of vague, like, how would you help this student? And so you have to be really careful in the kinds of wording that you use for me to be able to understand whether or not you're really being able to talk to the student. First of all, when it says how would you respond to the student, it means you're going to have to write some words, okay? Because I know that sounds sort of obvious, but you writing down mathematics for me is really not what you would do to a student, right? I mean, you may show them some of those things, but you're going to use words to talk to them. So I want you to write down the words you would say. So that's one thing that you're going to have to do, okay? The other thing to do is to remember that if a student is misunderstanding something, there's often a reason why. Now, this student has the answer incorrect, okay? There's actually a reason why they think that this works, though. Any ideas? Do you guys, why would the student do this and think that this would work? It happens when? With multiplication, yeah. So this sort of ability to mark out the p's, or I'm sorry, are they doing p? N, they're marking out n's on this one, is something that we do in multiplication, right? And it works. It is appropriate and it is correct and it works. Now, just telling a student, no, it doesn't work for addition, it works only in multiplication, is not especially helpful either, okay? Because you haven't really shown them anything to make them trust that you're correct. You've just told them, hey, you're wrong, and it works over in this other situation. There's nothing wrong with telling them that. It's just not especially helpful to them. Okay, is everybody with me so far? So a lot of times, especially when there's a situation where the student is incorrect, a good example or a good way of showing them why they're incorrect is to show them a numerical example of when it doesn't work. So a few things here. So let me write down the kind of answer you might want to write down in this, okay? So how would you help the student? So I would tell them, so I'm going to actually write what I'm going to say to the student. If this were multiplication, you would be correct, or your method would work, or something like that. We'll say your method would work. But with the addition of n to the numerator and denominator, this isn't always true. Now, could it be true? Actually, yeah, it's possible. There are random examples that the student might create, and you're going to have to be like, wait a minute, it shouldn't work. Well, occasionally weird things the students do wrong actually work, so you have to be careful. So saying this isn't always true is a little bit more, it leaves you an out if they find something that does work. How's that? Okay. So what we do want to show them, though, is it doesn't always work, because that's actually what we're trying to show them, is that this method of canceling that n out, it isn't always going to be okay. So you want to create an example. Now, on this particular one, most examples you're going to create are going to work, and so that's really good. When you're creating examples, it would be a good idea to keep things simple. So using that 427 and 315 or whatever I had before, those are not simple fractions. But something smaller would work really well. So let's say, for instance, that you started with the values 1 over 3. Okay? So we're going to take the fraction 1 over 3. And we're going to compare that, we're going to add a value on top and bottom. So somebody pick a value for me to add on top and bottom. 1. All right, so we're just going to add plain old 1. So if I add 1 on top and bottom and I actually do the operation of the addition first, this gives me 2 over 4, which reduces to 1/2. Agreed? Now, if we had done what the student wanted us to do, what would we have done instead? Yeah, we would have that 1 over 1 not happen, basically, like we canceled it out, and we would have 1/3, which is what where we sort of started when we created our example. clearly these two are not the same. And a student will know that, right? I mean, you could draw a picture to show them that they're not the same very quickly. Draw a pie and you get half a pizza and I get a third of a pizza, and if the pizzas were the same size, who gets the most? Right? It's a pretty simple argument at that point. So a numerical example really is very helpful to show why something doesn't work. Any questions on that one? Okay, I'm going to show you a neat, unique application that your book shows with fractions. It's just kind of a little bit fun. So it says if we take the set of numbers equivalent to 1 over 3 and we graph them as points on an xy plane, xy axis, the numerator is the x-coordinate and the denominator is the y-coordinate, what type of graph will we get? So let's just take it a piece at a time. It's talking about a fraction 1/3, and it says that we're going to have equivalent fractions to 1/3. So let's just create a couple of equivalent fractions. So I can have the number 1/3. What's equivalent to 1 over 3? 2 over 6. One more.
4 over 12.
Let's make it 3 over 9 just so they're a little bit smaller. It'll help me to do the graph. It's a little bit smaller. And we're going to do one more that you probably wouldn't have thought to do, and I'll show you why we're doing it when we get to the graph. I'm going to write -1 over -3 just so I've got some negative values in my graph, because that's still equal to 1/3, right? Okay, so what we're going to do is we're going to graph these so that all of this on top are the numerators are the x value of the point, and all of these values on bottom, it tells you, are the y value of the point. So this has created for us several points, ordered pairs. 1, 3, that's the first one. 2, 6, that's the second one. 3, 9, which is the third one. And -1, -3, my fourth one. Okay, and we're going to plot them on an xy axis. Okay, we're going to see if I can pull up a grid. I do. I have one over here. All right, so I'm going to create an axis. I'm going to plot points. The first one was 1, 3, which puts me right here. The second one was 2, 6, which puts me here. The third one was 3, 9. And then the last one that I kind of threw in there at the end was -1. Move this up just a touch. All right, -1, -3. Over here. Now, we picked them because they were whole values. That's why we picked those numbers, right? But there obviously are values between 1, 2, and 3 along this x-axis that correspond to y values that would still give me a ratio of 1 over 3, right? So if I were to connect the dots, that would be appropriate. And what kind of a graph would this give me? What shape is it? It's a line. And even as I say that, I sort of cringe because it isn't exactly a line, but it has a lot of similarities to a line. So this is the line that I would get if I connected the dots and it all worked. But there's a problem on here that doesn't work. There's a location where I have a point that does not give me a ratio, that does not give me the ratio 1 over 3. What is it? 0, 0, right? This graph definitely goes through the origin, agreed? But if I use the value 0, 0, and I try to write 0 over 0, that's not even defined. And it's certainly not equal to 1 over 3. Agreed? All right, so our graph that we get, let me go back to the screen over here. It says, what type of graph would we get? Well, this is a line, but it will not include the origin. Another way you could say it is that there's going to be a hole in the graph at the origin. We're going to actually have a place in the origin right here that doesn't work. There's a hole there because I don't really have 0, 0 on this line. But every other point on the line works just fine. Okay? So we have to be a little bit careful. We don't get, all of these possible values. We do have that one sort of problem swept. Any questions on that one? All right, this was the homework set, so go ahead and write those down in case, did anybody's, okay, you guys have all printouts that I gave you, so that should have printed out just fine. Did it print out just fine on your homework, on your sheet? Great, all right.